Hello students! Welcome to today's lesson, where we will explore an essential part of probability, the addition law. Let's start with a roadmap of our lesson for today. We'll begin by recapping the notations and concepts used to describe events and their probabilities. Secondly, we will be identifying the risk of overcounting. Through an example, we will see how simply adding probabilities can often lead to overcounting. We'll understand the idea of the intersection between two sets and why we need to subtract this intersection when adding probabilities. Then we will be introducing the addition law of probability. We'll apply this formula to different situations, including both mutually exclusive events and non-mutually exclusive events. Finally, we'll touch on the significance of independence in probabilities. So let's get started. Suppose we have the 10-sided die shown on the right. Consider events A and B. Let A be the event of rolling a prime number on a 10-sided die. The prime numbers between 1 and 10 are 2, 3, 5, and 7. Let B be the event of rolling an odd number on the same die, so we have 1, 3, 5, 7, and 9. In probability terms, if we want to know the probability of rolling either a prime number or an odd number, we write this as PA union B. Now let's look at an example to see why we can't just add probabilities without adjustments, using our previous events of prime and odd numbers. Start by calculating the probability of event A. This is 4 out of 10, since there are 4 prime numbers out of the possible 10 numbers on the die. The probability of event B is 5 out of 10, as there are 5 odd numbers on the die. Adding these together gives us 4/10 plus 5/10 equals 9/10. However, if we list the outcomes of getting either a prime or odd number, you will notice that there are some numbers counted twice. In this case, 3, 5, and 7 are counted twice. This is what we mean by overcounting. We should only be counting these numbers once, but when we simply add together 4/10 and 5/10, we count some of the numbers twice. If we don't correct this, we will get the wrong answer for finding the probability of A or B. We can also understand this by looking at a Venn diagram. After drawing the two overlapping circles A and B, we can fill it in with the numbers 1 to 10. Notice that the numbers which are both prime and odd are in the intersection of the two circles. Also notice that the numbers which are neither prime nor odd are outside of the circles. Now let's see a visual example of why we can't just add probabilities without adjustments. Remember, we want to calculate the probability of getting A or B. This is given by this whole shaded green area. But let's see what happens when we just add A and B together with no adjustment. Highlight the circle A in the Venn diagram to calculate the probability of A. Since there are 4 numbers in this blue area, the probability of A must be 4 out 10. Highlight the circle B in the Venn diagram to calculate the probability of B. Since there are 5 numbers in this red area, the probability of B must be 5 out of 10. But notice that when we add these two shaded areas together to find the probability of A plus the probability of B, we have actually added the intersection twice. We added it once when we took the blue shaded area and once when we took the red shaded area. This means that all of the numbers in the intersection have been counted twice. And notice that these are the exact same numbers that we counted twice when we went through this example earlier. So this is a visual way of showing the overcounting. We will further explore these ideas in the video on Venn diagrams. To correct this overcounting, we need to subtract the probability of the intersection of A and B. This intersection is written as PA and B. Since it includes the numbers 3, 5, and 7, then PA and B equals 3/10. So the correct formula is the probability of event A or B is equal to the probability of event A plus the probability of event B minus the intersection, which we now know is the probability of A and B. If we now apply this, we find that the probability of A or B is equal to 4/10, which is the probability of event A, plus 5/10, which is the probability of event B, minus 3/10, which is our intersection. This gives us a probability of 6/10. We can simplify this to 3 over 5. Therefore, the probability of rolling a prime or odd number is 3 out of 5. This formula that we have introduced is known as the addition law and is fundamental to the theory of probability. Now, there are a few important points to cover. There are examples where, in fact, the probability of A or B does equal the probability of A plus probability of B. This is not a violation of the addition law. Rather, it is a special case that occurs when the probability of A and B is equal to 0, in which case the events A and B are called mutually exclusive. This basically means the chances of A and B happening at the same time is impossible. On a Venn diagram, we represent this by the circles not overlapping, which shows that both events cannot happen at the same time. In this case, we do not have the problem of counting the intersection twice, since there is no intersection at all. For example, if we roll a die and A is the event of rolling a 2 and B is event of rolling a 4, then A and B are mutually exclusive, since rolling a 2 and a 4 on a single die roll is impossible. Here, you can add probabilities directly. We can write the formula like this: PA or B equals PA plus PB, so the probability of rolling a 2 or a 4 is simply done by adding the probability of each event. In this case, rolling a 2 or 4 is a 1 out of 6 chance, so we can do 1/6 plus 1/6 equals 2/6 and can be simplified to 1/3. This is the probability of rolling a 2 or 4. But remember, if the events can happen simultaneously, they are not mutually exclusive, meaning the probability of A and B is not 0. Then we need to use our previous formula from before. Another type of event you need to know is independent events. These are events in which the occurrence of one event does not affect the probability of the occurrence of the other. For example, the probability of raining in Dubai is independent of flipping a coin. For independent events, a special relationship holds. This is that the probability of A and B equals the probability of A multiplied by the probability of B. When we combine this with the addition law, we find that we can write the addition law for independent events as the probability of A or B occurring is equal to the probability of A, plus the probability of B minus the probability of A times the probability of B. Let's move on to some practice problems to see the addition law in action. Suppose we have a deck of standard playing cards and we want to calculate the probability of drawing a red card or a face card. Let's say event A is drawing a red card. The probability of this would be 26 out of 52 since half the deck is red. Event B is drawing a face card. This is 12 out of 52 since there are 3 face cards in each of the 4 suits. To find the probability of drawing either a red card or a face card, we want to find the probability of A or B. Remember from our discussion earlier that if we just add together the probability of A and the probability of B, we might be counting some cards twice. So the first thing we do is identify any overlap between red cards and face cards. The overlap occurs with red face cards, which are Jack, Queen and King of Diamonds and of Hearts. In total, there are 6 of these cards, as there are 3 in Diamonds and 3 in Hearts. Therefore, the probability of A and B is 6 out of 52. We can now apply the addition law. The probability of event A or B is equal to 26 over 52 plus 12 over 52, minus 6 over 52, which equals 32 over 52. This can be simplified to 8 over 13. Thus, the probability of drawing a red card or a face card is 8 out of 13. Let's consider another scenario involving a 6-sided die. We want to find the probability of rolling a number greater than 4 or an even number. Step 1. Identify the probabilities of events. In this case, event A of rolling, a number greater than 4 is 2 out of 6 chance. Event B of rolling an even number is a 3 out of 6 chance. Step 2. Determine the overlap. The intersection of numbers both greater than 4 and even is just the number 6, so the probability of A and B is 1 out of 6. Finally, apply the addition law. The probability of event A or B is equal to 2 over 6 plus 3 over 6, minus our overlap of 1 over 6, which equals 4 over 6, which can be simplified to 2/3. So the probability of rolling a number greater than 4, or an even number, is 2/3. By working through these examples, we see how to apply the addition law of probability to different scenarios. Remember to always check for overlap, and remember that if events are mutually exclusive, the overlap is zero. Keep practicing with similar problems to get comfortable with this concept. Did you know that the basic ideas of probability, including the addition law, began with the study of gambling? In the 1600s, French mathematicians Blaise Pascal and Pierre de Fermat exchanged letters to solve gambling problems, laying the groundwork for probability theory and helping us understand the likelihood of different events happening. In the early 1700s, Swiss mathematician Jacob Bernoulli expanded on their ideas and wrote Ars Conjectandi, which further developed the field. The study of probability continued to evolve, with mathematicians like Abraham de Moivre making significant contributions in the 18th century. This eventually led to the formal foundations of probability theory being established by Andrei Kolmogorov in the 20th century. In today's lesson, we delved into the addition law. We began by understanding the notations and concepts used to describe events and their probabilities. We then examined the risk of overcounting when adding probabilities directly, highlighting that simply summing the probabilities of A and B can lead to inaccuracies if there is an overlap in outcomes. To address this, we introduced the addition law of probability, which corrects for overcounting by subtracting the probability of the intersection overlap of events A and B. We applied this formula to our example to find the correct probability of rolling either a prime number or an odd number on a 10-sided die. We also discussed when to use the addition rule, distinguishing between mutually exclusive events which cannot happen simultaneously and allow for direct addition of probabilities, and non-mutually exclusive events which can happen simultaneously and require the use of the addition formula. Additionally, we touched on independent events, where the occurrence of one event does not affect the probability of the other. Finally, we worked through some example to help solidify your learning. Well done, and see you next time.